Okay, today we're gonna talk about risk. Let me see. Here it is. Okay. Um, Obviously, we don't have any idea about the future. However, we can look at the past data and have an idea of how the returns are distributed. Something we have already done here. Okay, we have until now calculated only the expected return, which we call also average return, which I remind you for the second time, it's based on the data of the past and it's not a forecast of the future. But well, we'll consider it to be a forecast of the future, but you never know. Okay, but in finance, it's also important how much your investment varies, so oscillates up and down. Because for several reasons, some people don't tolerate the fact that it goes up and down. Some people would like to sell early and so cannot wait too much time. And so if it goes up and down too much, it could go down and stay down for a lot of time. So in general, people don't tolerate too much up and down, so we want to measure it. This is called risk, and it's basically the standard deviation of the returns. Not the return of the returns. Okay, in our case, it will be the standard deviation of the daily return. So you have to have returns at a very small scale, in our case the daily returns, and calculate its standard deviation. Its average eventually analyzed. It's the average return or the annual return, and the risk is the standard deviation of the returns. Okay, it's also called volatility. Okay, so let's consider, for example, this for returns. In this case, we don't use a daily return. Suppose we use an annual return. Okay, so we have two stocks, one with an annual return of 15, 20, 0, 0, 5, 10, and another one with an annual return of 35, 30, 40, minus 0.05. Okay, which one would you prefer? Well, oops, what happens? PD is not defined. Oops, import pandas as PD. Okay. Which one will you prefer? Well, stock 1.mean, this has an average return of 10%, and stock 2. Please note that if I do something like this, it will display only one. I do a little trick here, so it displays both, even with a print. Okay. Okay, 0.1, 0.1. So their expected return is exactly the same. They both return on average 10%. However, the standard deviation, STD, is very different. One has a standard deviation of 0.10 and another one of 0.33. Well, it's evident from here. This one is more risky. So, given the same expected return, people usually prefer this one. Okay, given the same. Then, if the expected return is different, you may choose how much volatility are you able to tolerate. We can, as we have already seen, put them together into a portfolio, okay, equal 0.5 by stock 1 plus 0.5 by stock 2, okay, and portfolio mean, okay, 0.1 obviously, portfolio mean, portfolio stood, and look at the surprise. The standard deviation of the portfolio, the return is the same. The standard deviation of the portfolio, on the other hand, look, it's not a halfway in between, but it's much closer to this one rather than to this one. This is generally true if you choose the two stocks which have a low correlation. So when one goes up like here, the other one goes down, or like here, or like here. This is the second, third, and fourth year for these two stocks is a typical example. When one goes up, the other one goes down. Probably these two have even a negative correlation. So that's why. So if you choose the stocks in your portfolio with a negative or at least very low correlation, you will have the surprise that the volatility or the risk of your portfolio, it's not a halfway in between, but it's much closer to the one with the lowest risk. Okay. Clearly, in this case, it doesn't make sense because the one with the lowest risk has the same expected return, but usually the one with the lowest risk has also a lower expected return. So you put them together, you get an expected return which is exactly away in the middle, but the volatility is much less than the middle point. Okay, so let's make a real example here as usual. Oops, here, sorry. Import YFinance as YF. Open. Okay, we get two stocks which behave completely different, Procter & Gamble and Microsoft. So we get the prices. Tickers start equal 195.11. Adjusted close. Take a look at them always. Okay, let's do all these exercises using the log returns instead of the simple return, just to add some variations. So log ret and numpy log of prices divided by prices.shift 1. Okay, there are two formulas. One is this one, the other one is with a minus. You should know both of them. Thank you. Okay, as usual, the first one is none. The other ones are all valid ones. Okay. Okay. Microsoft much more than Procter & Gamble. So we take, this is the average daily return. This is the annual return. 28% for Microsoft and 10% for Procter & Gamble. Not bad, I have to say. And let's see the standard deviation. Standard deviation, Microsoft 3 times as risky as Procter & Gamble. Not exactly 3 times, but almost 2 times and a half, let's say. Okay, now let's build our portfolio. I call it P, okay, and P dot of the prices, not a log ret. So let's build it directly with the log ret. Log ret multiplied by, we build an equally weighted portfolio. Okay, let's take a look at it. Okay, fine. Let's calculate. Oops, the usual problem. Can we get rid, sorry, starting from here, I get rid of the none at the beginning. Okay, so now I don't have any problem anymore. P.min, P.stud. Okay, and you can see that perhaps by 250 to have a look at it better, 90%, which is exactly halfway between Procter & Gamble and Microsoft, exactly halfway. Okay, and here instead the risk is 0.02, which is not halfway between this one, but it's closer to Procter & Gamble because they have a low correlation. Are we sure that it's closer to this one? Let's see. I calculate it by hand. Okay. Yes, because the point in the middle is 0.026 and instead the risk is 0.020. So it's better than the point in the middle. So the return of the portfolio is the point in the middle, but the risk is better. Very well. Why? Because they have a log correlation, logret.core. Core displays the correlation matrix. Clearly the correlation between Microsoft and itself is 1, not surprisingly. And the correlation between Microsoft and Procter & Gamble is 0.09, very low. I can tell you, usually in the stock market they range about at least 0.3. Okay, it's very rare to find a negative correlation. Most of the correlation are 0.3, some up to 0.8. Okay, adjusted for your information, I tell you the covariance matrix. If the ones who have studied statistics, I hope all of you know what is the covariance. I just tell you how to calculate it because we'll need later. Okay, all this has been calculated if you know the logret day by day, because can you see I calculated here the logret of the portfolio knowing the logret day by day. Okay, so in order to do it you must know the logret day by day of both stocks. Okay, can we simply calculate the return just knowing these things here? Well, yes, because the return, sure, because it's just the average of these two. Can you see here? 0.10 and 0.28, and here it is, where is it? 0.19. It should be the average of these two. Okay. So for the return, we can calculate the return just simply without knowing all the daily returns, which is much better. Imagine if you have 2000 stocks. You cannot have the list of each one, all the data for each stock, and do the metrics and blah blah blah. You just have the yearly return, and you just calculate the return of your portfolio very easily. For the risk, instead, it's not so straightforward to calculate it from here, but we can do it with the help of the covariance matrix. So let's see. So, in general, as you've seen before, the portfolio return, the daily return, but also the annual return is nothing else but W1, so the weights of the first one by the return of the first one plus the weights of the second one by the return of the second one. So easy peasy. So portfolio annual return, PAN, portfolio annual return, it's nothing else but the let me see, but the wait, logret.min okay, this 2 multiply by the weights which in this case are 0.5, 0.5. So portfolio annual return, PAN. Let's see the result. Sorry, numpy dots. Okay. So the matrix multiplication of the weights by the returns. Okay. So portfolio annual return. Okay, but let's leave it like this. So you can see now here, without knowing the single logret, but knowing only the average logret, if you don't trust me, you can put so logret min in a separate file, separate variable, logret min. Okay. Now in a separate variable I have the okay. Now if I have only the returns, okay, this information here, I can calculate this is the average daily, then you just multiply by 250 and you get the average year, not the yearly one. You can do it here. You can do it here. In this case, you don't need to do it here. So I have the yearly returns and just 90%. So it's very easy, as we have seen before, to get the portfolio return if you just know the average returns or the yearly returns of the stocks which are inside. So you don't need all the daily data. Okay. For the risk, it's difficult because it's not so. You can see the difference. It's not so easy. It's not simply the weight by the risk plus the weight by the risk. No, unfortunately, absolutely no. The formula is much more complex. It's this one. The ones of you who have studied statistics will perhaps remember the formula for the covariance. The ones of you who have studied mathematics, not at university, but probably in the first year of high school, will remember the formula for the square. So a plus b square is a square b square plus 2ab. Okay, the formula is more or less that one. Okay, so the variance of the portfolio is something more complex. Can you see? Much more complex. The square of the weight by the variance of the first one, so not the standard deviation but the variance, which is the square of the standard deviation, the square of the second weight by the variance of the second one, plus 2 times the weights of the first one, the weights of the second one, and the covariance, which is this thing here. No, the covariance is this thing here. Okay, so it's not easy. You can represent in a matrix format in this way. This is the covariance matrix. This one, the covariance matrix. The covariance matrix contains here and here the variances, which are the square of the standard deviation. So these are the 2 variances, and this is the covariance. So this is the covariance matrix. If you multiply it by W and W, you get variance 1, W1, covariance 1, 2, W2, covariance 2, 1, which is the same. W1 plus variance 2, W2. Okay? And if you multiply again, but this time in front, with the weights, you do all the mathematical calculation, W1 by variance 1, W1, W1 by covariance, W1, W2, W2 by W1 covariance, W2 by W2 variance. I invite you to do the little calculation if you wish, and at the end you get exactly, oops, it goes out from the screen, exactly the formula above here, this one. So the variance of your portfolio is nothing else but the weights in the horizontal direction, matrix multiplication with a covariance matrix, matrix multiplication with the weights. Or better, first do this matrix multiplication here, so the covariance matrix with the weights, and then this other matrix, or better, vector multiplication. So with this form, we have seen it in the case of 2 stocks. In the case of more than 2, it's much more complex, but the formula remains the same. Okay, so let's see it. So now I want to have only the weights, which in our case 0.5, 0.5, okay, the covariance matrix, which in our case, where is it? It's this one, and nothing else. Okay, nothing else, and with this information only, I will calculate the variance of the portfolio. Then its square root is the standard deviation, which means it's the risk. Okay, let's see. So no other information. So print, better. First of all, let me calculate numpy dot. I will do it step by step. Cov m, comma weights. Okay. Okay. Then again another numpy dot of weights, comma this one. Okay. So this formula here is this one. This weight should be transposed. It means should be reversed from the vertical to horizontal direction. However, Python doesn't care about vertical or horizontal direction. Understand it anyway, don't worry. Weights. Here the result. But don't forget that it's the variance. We should calculate the square root to get the risk, because the standard deviation is the square root. So NumPy sqrt, I hope it's sqrt, let's see. Yes, and let's see, 0.0208, where is it here? 0.0208. So it's possible to calculate the risk of the portfolio without using all the daily returns of each stocks inserted in the portfolio. The only thing that you need is the covariance matrix and the weights, clearly. Where is it? I lost it. Here. So the only thing you need is the covariance matrix and the weight. That's why very often in people who do this analysis seriously, you see the list of the stocks that you have to consider, and you don't have the daily return of each one, but you have very simply the annual return of each one, and then a big covariance matrix. In this way you are able to build any portfolio with those stocks simply using these formulas here and calculate the return. Where is it? Here. This is the weight, okay, and even the risk using this formula here. Okay. Very well. Now we make a little distinction, which I will tell you will not work always, so don't worry if in your home exercise it will not work, just try to justify, between the systemic risk and the diversifiable risk. Okay. This formula here can be split into two parts. One part is this one. So you can see the formula is this one, and can be split into this part here and this part here. This part has the covariance in the middle. So it depends on how the two stocks are related together. This part doesn't have the covariance, so it's independent on how the two stocks are related together. So we'll call this part the systemic risk, and this part the diversifiable risk. This part can be sent to 0 or even to negative value, but let me see, it can be really sent to a negative value? Yes, because covariance can be negative. So even to a negative value, okay, if you manage to choose the right stocks. So the diversifiable risk can be sent to 0, even to a negative value, okay, and this part you cannot do anything about it. It depends on still depends on the stock that you choose, but doesn't have anything to do about, doesn't have anything on the relation of the stocks among themselves. Okay, so we will distinguish in the sum of the weight of the square of the weights by the variances, which we call systematic risk, and the rest, which is calculating the rest is a mess, so we cannot calculate with an easy formula from here. So we calculate it simply with the variance of the portfolio minus the systematic risk, which is the diversifiable risk. It could be in some situations negative, but really rare. Okay, so this one cannot be reduced, or better, it depends on the market. It still depends on the stocks that you choose, but it depends mostly on the market. And this one can be reduced choosing the stocks which have a certain relation about them. Here, beware that we are talking about variances and not standard deviations. So it's not really risk. The risk is the square root of it. Okay, but still gives you an idea about if this one, for example, if this one is too big, especially compared to this one, it means that you can pick the stocks, pick other stocks, or pick the stocks in a different way, perhaps, and still reduce the risk. Okay, let's see in our example. Okay, so systematic risk. I call it risk, but it's not really the risk because it's the variance. Okay, np dot the square of the weight, so weights square multiply by the variances. I have to calculate the variances before. So I can take the variances from the covariance matrix. Okay, so I could take the variances because the variances are the diagonal of the covariance matrix. So the diagonal of the covariance matrix are all the variances. So I could take them from here, but I can take them also from log ret logret dot iloc one colon dot var. Okay, let me first check this one. Okay, it works. And then variances. Okay, that's it. Error. Don't worry, I knew it. I tried the exercise before. Why the error? Well, the error it's because unfortunately weight is a list. It's a list, and you cannot make the square of a list. Python is not so intelligent. You cannot even do it something like this. Okay, but we can still have a trick. We can do the numpy dot also here. Okay, so we can have this dirty trick. Okay, in this way we calculate the weight square. Okay. Okay, and the diversify, let's call it diver risk equal, and it's the risk before, so this one minus the systematic risk. I never know whether it's systematic or systemic. Oh, okay. Okay, let's print everything. Print. Oops, why do I get two values? There is a mistake here. So this numpy dot, let me check what does this numpy dot do. Okay, no, it doesn't do what I was hoping for. Sorry. The trick is another one. MP power. Okay, the trick is this one. Sorry, wrong trick. Okay, so this is the systematic risk and this is the diversity. Just to have a better look at them, I multiply by 1000, otherwise the numbers are too small. Okay, this is 0.420, so we have a lot of diversifiable risk. It means that we could choose them even much less correlated. So if we were able to choose, for example, with a negative correlation, okay, and so this is all the risk that we could send to 0. So there is still space for improvement in our portfolio. Okay, that's it, and bye bye.